My name is Ken Oman. My wife and I started the Cure Starts Now chapter out of Somerset, Massachusetts, in memory of my daughter who passed away 10 years old. She had DIPG. She battled for 8 months, had a pretty rough 8 months. So very much appreciate what you're doing. I know we want to talk about the grant, but before we start, I wanted to let you know that the DIPG DMG Collaborative has decided to award you with a $40,000 grant towards your studies for CXCR 1 and 2 signal pathways.
Okay, thank you very much. I appreciate it.
Dr. Behar, obviously we've spoken via email thus far and learned a little bit about your project and everything. And, from the DIPG DMG Collaborative, that's 27 partners. And from the chapters of the Cure Starts Now, we have 52 chapters as well. The support comes from 4 different countries. And certainly we're excited to see what type of work you do here with DIPG and are very excited about seeing this project move forward. So just wanted to say congratulations from that perspective.
Thank you.
Thank you. And I know Erin also wants to share her thoughts and some other information.
Hi, Dr. Behar. My name is Erin Slifka, and I am the founder of the Ayla Foundation, which we started in honor of our daughter, Ayla Grace, who battled DIPG for almost 12 months and earned her angel wings in June of 2022. So it's a privilege to meet researchers such as yourself who are working to make a difference in the lives of all the children and families who are battling pediatric brain cancers. So I do have a question. In your grant, you talk about how tumors may more easily spread in brainstem tissue and the potential of the CXCR1 and 2 pathway to enhance this. So how do you see your project impacting this growth and spread problem?
Okay, so I guess if you think about a tumor, there are 2 things that eventually succumb the patients. One is the proliferation, obviously, but maybe more severe is the invasiveness to the tissues around. I mean, if you talk to pathologists, you'll tell you that they're just shooting into the tissue. And obviously, it's a huge problem. And I'm not pretending that I have, the cure or hopefully part of the cure. I mean, it's a very complex problem, but we notice that if we take sections of very young mice, presumably it's mice, it's not human, but if you take pieces from the brainstem and compare that to pieces of the cortex. At the same time, you inject the tumors, and you just see how they behave. Now, again, it's not human, but evolution is there. And there are many shared things between mice and human, although they don't look the same. So you can see that it's really striking how different the same tumor at the same time behave in these 2 tumors. So, and that, led us to try to see what kind of cells are contributing to that. And part of the work that we published was that microglia from the brainstem are different than the one from the cortex. And we identified a number of factors. We are working on some of them. One of them is CXCL5 that we noticed that is more highly expressed both in human patients samples, and also if you take cells from model cells and you inject to the brainstem or the cortex in parallel, the same cells. In culture, they are the same. You inject them, after a day, you check them, and you see differences. Like the receptors for CXCR1 and 2 are much higher in the cells that were injected to the brainstem. So we think that there is something going on there. There is a communication between the tissue, this specific tissue at this specific time, and the cells. If I can show you if you would like one image very quickly. So I just wanted to show you one image. Can you see here
Yes.
the image? So you can
We
see
can.
here cortical cells so we developed this method where we inject a cluster of cells in the same size, either to the cortex or the pons of young mice. It's around day 5 or 6. And then we have, using a specialized microscopy, we can monitor them live. So this is an image at day 1 after injection, and this is the same in the pons. And then there is how the tumor behaved in the pons compared to how it behaves in the cortex. And I think it's quite striking to see how different they behave. Although it's the same cells coming from, the same culture, somehow they recognize the environment, they are happy, they are more happy. We also show that they are surviving more and proliferating more. So something is there. Now, regarding the CXCL, so as I mentioned, they are more highly expressed there. The receptors are more highly expressed in the DIPG in patients, and also when we inject the cells to the pons, we see that the receptors are going up. There is also another study by Chris Jones that I'm sure you know. He's funded by your group. In one of their many works, they found that there is a subpopulation of cells. When you take the DIPG models, you see that some cells are more invasive than others, and they identify factors. And one of the factors that were quite prominent are CXCL2 and 3, which are again working on the same receptors, the CXCR1, 2. So there are a number of hints that maybe this system is involved in the behavior of the cells in this specific place. And we also have some results showing that if we use the inhibitor, at least in culture, we see a reduction in invasive behavior of the cells. So I guess we would like to test both in vitro, in slice cultures, and after that, we would like to go to model mice and see if we can affect. But I just need one caveat is that I'm not sure that the inhibitors that are available and that are in clinical trials, that it will pass the blood-brain barrier. It's an issue. It's not simple. Therefore, we are planning first to start with shRNA to the receptors. So just as a proof of concept that they somehow will affect the behavior of the tumor in the pons.